Greetings and welcome to the video on standard error of the mean. I've gone ahead and put the title of our brief little lecture here on the canvas, and I've drawn two distributions. And what I would encourage you to do at this point in time is just perhaps pause the video for a moment and see if you can identify what these two distributions are on your own. So why don't you go ahead and do that now. Okay, so if you've paused the video and taken a moment to look at these distributions, what you'll notice is that the one on the left here is actually plotting the frequency of these raw scores. So this is our frequency distribution here. And then this one on the right is plotting the frequency of X bars. When you're plotting the frequency of X bars, then we know that we have a sampling distribution over here. Okay, let's just give a little bit more information here. Let's just say that this frequency distribution on the left is a sample of n equals 25 individuals pulled from a population, and we measure, say, the mean age, their mean age, and it falls here. And that X bar, let's just say that X bar is from this sample is 27. And then let's just say that the standard deviation, I'm making these numbers up right now, I don't have a data set in front of us, is 15. So what that means is if we went to kind of the -1 and the +1 standard deviation around this, we know that we would capture approximately 68% of the individual raw scores would be inside of this particular interval around this X bar. Okay, with that in mind, now what we need to do is kind of talk about how this concept relates to a sampling distribution. When we're dealing with raw scores, we call this the standard deviation, but when we're talking about a sampling distribution, we can still get a mean here. Let's just say we have a middle point, and what does this mean represent? Well, the mean to the left was the mean of the XI scores. We can still get a mean here, but this is a mean of what? A mean of sample means, where we have replicated an infinite number of times, n equals 25, and we repeat this, say, an infinite number of times. We get a distribution, we get the mean of that distribution, and that mean is based on sample means. So the heaps of scores here, if you will, just trying to draw these in here. The heaps of scores here, these are means from an infinite number of repeated experiments where we have drawn 25 people from a population, gotten what their mean age was, put those 25 back in, took another 25 out, and so on and so forth. We do that an infinite number of times. We get a mean. Well, if we get a mean, we can get variability around this mean that's just like a standard deviation. Those weren't equally spaced. Let's try that again. Let's go +1, -1. But instead of calling this standard deviation now, what we do is we call this the standard error of the mean. Actually, we'll just draw this up here. So this standard deviation is referred to now not as standard deviation. Standard deviation refers to the variability of the raw scores around an X bar. The standard error of the mean is now referring to how these individual sample means vary around the mean of the sample means. So it gives you a variability of what the means could be in the population. And again, this would capture 68 kind of percent here. So let's go over what the I guess kind of the theoretical background. If you wanted to calculate the variance for this, sigma squared, and we're going to denote the variance of the mean by putting this x bar as a subscript, would be what? Just calculating the variance of this distribution divided by n. We're using n, not n minus 1, because we're talking about the population. And this would equal the variance of the sampling distribution of the mean. But remember that this has squared units here. I'm just going to put an asterisk right here. This is squared units because we're squaring these values. And so we need to take the standard deviation. So the standard deviation is this. So it becomes the square root of the quantity we were just talking about. But instead of calling this the standard deviation, we call it the standard error of the mean. Now you might hear this, you might see the alternative names, you might see it as SEM, you might just hear it called standard error, but it's really the standard deviation of the sampling distribution of means. That's what the standard error is. But remember, we rarely know what the population parameters are, and since we rarely know, we need to use point estimates. And so when we're talking about point estimates, this value, the variance of the sampling distribution of means, becomes this, because we're going to use the variance of our sample as the point estimate. And then the population parameter for standard error of the mean will become this quantity. And so from our example, this example here, the standard error of the mean, had we just done this first experiment here where we pulled 25 individuals from our parent population and calculated their mean age, we could calculate the standard error of the mean as the following. I'll just do it right here. Standard error of the mean then equals 15. Why? Because 15 is the standard deviation, right? Divided by the square root of 25, because we took this as an n of 25. And so the standard error of the mean is 3.0, and it still has units. So if this mean here is in years, this standard deviation here was in years, this is going to be in years as well. And so how do we interpret this? Basically what this is saying is, if a random sample of n equals 25 observations was drawn from a population, which is what we did right up here, big asterisk, and the mean was computed, this right here, which we did, put it in blue, and the mean was computed, which was 27 years, and then we repeated it an infinite number of times. That is this scenario over here. The standard deviation of that distribution, the standard deviation here of that distribution, can be calculated without having to go through repeating it an infinite number of times. We can calculate it based on this equation right here. And I just noticed that that equation was off. This should be the square root of n. Apologize for that, but we caught it. Right, and so it can be calculated without having to do all this a repeated infinite number of times. We can calculate it based on using our point estimate from our sample, which was the sample standard deviation divided by the square root of n. We did that right here, and this was our answer. And so what we're essentially saying then is that if the mean here was, I'm just going to use an eraser just here for a second. Let me just kind of erase through the magic of digital stuff here. If we said the mean was 27 as our point, that's 25. If the mean was 27, all right, try this one more time. If the mean was 27, that was our point estimate of what mu might be in the population. We would expect 68% of the sample means, had we repeated this an infinite number of times, to be between 30 and 24. And so it gives you, the standard error then gives you essentially kind of an estimate of what the variability of means could be in the population, whereas the standard deviation is giving you a sense of the variability of your raw scores around your central point, your sample mean. That sampling, or the standard error of the mean is giving you what the variability around your point estimate for mu might be. So again, frequency distribution, you can get a mean, a standard deviation. Sampling distribution, you're taking your point estimate from mu and you're creating an interval around it, saying these are the values that mu could take on if you were to replicate this. Plus or minus one standard error would give you essentially 68% of the total, would capture 68% of the possibilities that X bar could take on in the population. So hopefully that hasn't muddied things up too bad. The big take-home message here, the big concept to take home, is that you've got two distributions: frequency distribution, sample distribution. On the frequency distribution on the left, you're calculating sample statistics. We can get a mean, variance, standard deviation. The sampling distribution's on X bars. I think we've driven that point home. You can still get a mean of all of those sample means in that distribution, but when you want to calculate the variability around what that point estimate for mu might be, we don't call that a standard deviation anymore. We call it the standard error. And when you're dealing with means, we call it the standard error of the means. So that is really the big take-home message, and from this we'll build on to two final concepts that use this information, and then hopefully move on from here further into our story about inferential statistics. So thank you for watching the video, and we'll have some other supplemental material in the module to help with this.